Hydrostatic force, we need to, when dealing with water, we need to use the fact that water weighs 62.5 pounds for every cubic foot that you have. This trough is 8 feet by 8 feet. In theory, what you do is say, well, take a rectangular strip, find the area of this strip. So usually this width would be called delta x when you're going left to right, but this is going to be going up and down, so I'm going to call it delta y. And find the area of this strip, multiply this by area, and you will have pounds per foot. The other thing you need to consider is how far underwater is this rectangular strip. So what we could do is say this is going to be the x-axis, this is going to be the y-axis, and if you go from the x-axis up, that is a length of y. Since this is going from 8 down, this length is 8 minus y. So if we then multiply by that 8 minus y, which is in feet, all of the feet will be canceled and we will have pounds, and that's going to be the total force in pounds. Okay, so we need 62.5. The next thing to do is multiply by the area of this rectangle. So its length is always 8. That does not change. Its height is delta y. And then we need this last idea that this is being held underwater. So this is a depth of 8 minus y. Now that's going to be the amount of force that is on this red rectangle right here. What we then have to do is have that rectangle go from the bottom to the top and add all those up. So this is the adding, and then go from 0 to 8. Technically, when you do the integral, this becomes dy, so we would actually have dy 62.5 times 8 is 500, so I could take this 500 and factor it out, and then integral, so this is the dy. So actually what we're integrating is just 8 minus y from 0 to 8. So the 500 stays there. This is going to be 8y minus y squared over 2. Evaluate from 0 to 8. The 0 will actually contribute nothing to the problem. We've just got a 64 minus a 64 over 2. So once we reduce it, this becomes a 32 times 500, which is 16,000, and that would be in pounds.